Okay, we are off to chapter 4. So obviously this is new material for exam 2. Exam 1, again, as we talked about, is going to be on Wednesday uh, during lecture time, obviously. So, all right. So chapter 4, going backwards there from chapter 10. We're talking about elements, atoms, and ions in this chapter. We're going to talk about really sort of important experiments that help us get an understanding of sort of the atom and what makes up the atom. We'll also talk about some properties of atoms, like mass numbers, atomic numbers, and so forth. And then we'll actually get into some periodic table, I think, in this one as well. And obviously talk about ions. First off, though, let's talk a little bit about formulas of compounds. A compound always contains the same relative numbers of each element. And a couple of things about a compound, as we probably talked about previously, but just a reminder that we have basically elements, which are really your sort of basic units that are represented by atoms. They're really as far back as you could go. So an atom is a basic representation of an element. Then we also have molecules, and we also have compounds. And sometimes people, again, uh, have a little misunderstanding about sort of the difference of the two. So when we talk about molecules, molecules are really just a basic definition of two or more atoms together. And that is really just the definition you need for something to be considered a molecule. It's just that two or more atoms together. And that is different than a compound where you need two or more atoms of different elements. And that is the sort of difference there between those two. A molecule can be two or more atoms of the same element. A molecule could be two or more atoms of different elements. A compound can be two or more atoms of different elements only. It cannot be the same element. Otherwise, that's just going to be a molecule. So that is the difference between those two. So, for example, water always contains two hydrogens, one oxygen. And just an example of that, for example, here we have H2. That is a diatomic molecule. That is how hydrogen normally exists. You saw the other day in the lab, last week in the lab, as it was bubbling there, and you kind of lit on fire there with your wood splint. That is hydrogen gas. Now, hydrogen is definitely a molecule because, again, it is two hydrogen atoms together. So it meets that definition of a molecule. Hydrogen, though, is actually not a compound because both atoms here are the same element. So it is not considered a compound. It's actually considered, in this case, an element. And that is because it basically has only atoms of the same element involved. So we have only hydrogen atoms involved here. That's an element. And because it's two or more hydrogen atoms together, it's considered a molecule, but again, it is not considered a compound. While water, on the other hand, here, which is basically H2O, basically three atoms together. So that is also a molecule because there's two or more atoms. It is also a compound because it is made up of both hydrogen atoms and oxygen atoms. Water obviously is not an element because it is made up of atoms of different elements. So that is the difference there between those three things, basically. Any questions on that there? So when we do have a compound, regardless of where we get it from, it should always have, again, the same sort of relative numbers of each of those things. And one of the ways that we do represent a molecule or a compound is with a chemical formula. And in a chemical formula, we use the symbols and we use really a subscript to represent how many atoms of each of those that are present. So when we look at the formula here again for H2O, the subscript always goes to the atom to the left or the element to the left. So that would mean we have two hydrogens here. And if there is nothing written, much like in chemistry here, if you do not see anything written, it's assumed to be one of something, and that would give us our one oxygen. So when we always write a chemical formula, always subscripts, little numbers, goes to the guys to the left there to represent, again, how many of each of those atoms of those elements we have. So again, we use our symbols. As we'll talk about, symbols can be either one letter or two letter symbols, but we do use our symbols. So once again, as we just saw there, two hydrogens there, one oxygen, nothing written there, one carbon, two oxygen atoms, one nitrogen atom, and three hydrogen atoms in this particular case, in the case of ammonia. So why don't you take a moment here and write the formulas that sort of describe these descriptions. Bless you. Okay, so let's take a look. So we have a molecule that contains six carbon atoms and six hydrogens. So symbol for carbon is a C. We put a little six next to it to the right, and H is hydrogen, and a six there to the right of it. Next one is a compound that has half as many calcium as there is chlorine. So calcium is Ca and chlorine is Cl. And if we have half as many calciums, so we'll just go 2 there for the calcium, and that will give us one, I'm sorry, 2 for the chlorines and 1 for the calcium in that case, which would be half. By the way, it always has to be whole numbers there on the bottom. You can't have like a half atom or anything like that. So all these subscripts that are on the bottom always has to be whole numbers. Again, it can't have, like I said, a quarter of an atom or a half atom. It's got to either be a full one or multiples of that. That would be why we wouldn't want to do something like calcium 0.5 and obviously chlorine 1 or anything like that. A compound contains equal numbers of sodium. Sodium is Na, and nitrogen is N, and 3 times as much oxygen. So if we have 1 of sodium and 1 of nitrogen, that would mean we would have 3 times as much oxygen there, and that would give us something like sodium nitrate, which is what that is. Calcium chloride on the second one as well, and a little benzene organic guy there on the first one. Any questions on formulas? So numbers on the bottom tell you how many atoms of each element. Again, always goes to the guy to the left. Later on, we'll see they also represent some other sort of chemistry type of units, like moles of each of those elements as well. So we'll talk about that in a later chapter as well. All right. So then let's get into the actual heart here of this chapter, which is about the atom. And again, we're going to go through some experiments, some things that kind of occurred along the way. And again, we'll kind of point out some things that you obviously need to know from these sort of experiments and what was going on. So let's first talk about sort of the atomic theory and the idea of what are atoms, what makes up atoms. So obviously it started a long time ago. There was a belief that matter was composed of these very small, indivisible type of particles, indestructible sort of particles, which are named atomos, sort of a forerunner, obviously, to atoms here. And A lot of things were sort of apparent to scientists along the way. Excuse me. That most sort of natural materials were made up of pure substances. Pure substance, like we kind of did in the lab last week, right, is something that is obviously a substance that is by itself, not mixed with anything. So water by itself, right, is a pure substance. Salt by itself, a pure substance, and so forth. Pure substance can either be elements or compounds. There's a law of composition, which means that for every compound, there's always the same composition, regardless of, again, where it comes from. So if you take something like water, which is basically two hydrogen atoms and one oxygen atoms, the mass of hydrogen is about 1. So you got a roughly 2 grams of hydrogen there. The mass of oxygen is roughly 16 grams. And that means that for every 1 gram of hydrogen, if you divide it 16 by 2, you got about 8 grams of oxygen present in every water that you basically make. So there's always the same ratio, if you will, of the mass of one element to another. And that's what is sometimes referred to as the law of composition. Again, you get that really just by dividing them by 2, right? Now, one of the early sort of atomic theories was one that was done by a guy named Dalton. John Dalton was an interesting guy. He kind of kept records of the weather for most of his life. He would just write it down every day. He never got married, but he did like to go bowling on Thursdays, which, again, if you learn nothing else in this class, that is probably the take-home message there. Will probably be on the most exams after the first exam. Um, we do, though, find out that he's a pretty not great lecturer, but he was a good little tutor. But one of the things he was able to sort of come up with was a definition of sort of what we call atoms. And there's several parts to Dalton's atomic theory, and we're going to talk about the different parts here. And you do need to know sort of the parts of Dalton's atomic theory. Now, remember, as we also talked about maybe earlier on as well, a theory is something that may not be correct in all aspects of it, and that also holds true for Dalton's atomic theory. There are certain parts that are good, and there are certain parts that maybe are not so true anymore. Again, remember, a theory is something that maybe can be later proved not correct in all aspects of it. And that's different, again, than something that's like a law of conservation of mass or something of that nature. He said that elements are composed of these extremely small particles, these sort of indestructible type particles, which are called atoms. And all atoms of a given element are identical to each other, and they have the same size, they have the same mass, and they have the same chemical property. He also said that atoms of different elements do differ from each other in terms of their size, mass, and so forth. Now, in terms of talking about, what's sort of correct and what's not correct, this is one of the things, or a couple of things here that are not so correct. And the first thing here is this idea that all atoms of the same element are identical to each other. Again, meaning that they basically have the same size, the same mass, and chemical properties. This is sort of later disproven, if you will, with the discovery of something we'll talk about in this chapter, which are known as isotopes. And isotopes are the same element, but they have different masses. So obviously, if they have different masses, they cannot be perfectly identical to each other. They must contain something different than another isotope of that element in order to have different masses. So that is something that is not correct in terms of Dalton's atomic theory. Also, the idea that elements are sort of indestructible. You can, through, say, nuclear reactions, kind of destroy an element or make it into a new element. So, that part of it also is not so correct. This part is all good. The atoms of one element are different than the atoms of another. So again, if you have an iron atom, it is different than if you had a copper atom, in terms of things like protons, electrons, neutrons, perhaps. He also said that compounds are composed of atoms of more than one element. And that is true, as we just talked about. That is your basic definition of a compound. You do need to have different elements involved and atoms of different elements for it to be considered a compound. A chemical reaction involves only the separation, recombination, and rearrangement of atoms. We do not destroy anything in a normal chemical reaction, and that is true. So, as we talked about, I think, in the previous chapter as well, as we go from reactants to products, all we are doing here is breaking these bonds, and all we're doing on this side is making bonds. We absolutely, sort of positively there, because we are only playing with electrons, which we will talk about shortly, is nowhere in the nucleus. They're on outside of the nucleus. We do not change the elements. So if we started with 4 carbons, we will end with 4 carbons on the product side. Again, they may be in different compounds, but we will not lose a carbon along the way. So we never sort of change the elements that we start with in a chemical reaction, and we have that sort of conservation of those elements. That is why in a lot of cases when you do things like balancing equations for that reason, so we don't lose any elements along the way. That also, by the way, is different than in a nuclear reaction. In a nuclear reaction, the only thing you're doing pretty much is changing elements into different elements. So there is no conservation of elements in a nuclear sort of reaction. But in a chemical reaction, which is what we talked about in this class, chemical reactions, what you talk about in 1A, you have that conservation of those elements. In 1B, you'll get a whole chapter on nuclear chemistry. And in that chapter, you don't have that conservation of elements in those type of reactions. And because we do end up with really the same elements we started with in a chemical reaction, we have the law of conservation of mass, which says that we don't create nor do we destroy any mass along the way. And again, if you think about if we had 4 carbons to begin with here on our reactant side, we would end with 4 carbons on our product side. And because these 4 carbons are 12 grams each, and these 4 carbons are 12 grams each, we will have the conservation of elements. Yeah. Yeah, go ahead, you can grab it. Yeah, no problem. Yeah, no problem. So because we do have, again, like I said, that sort of conservation of the elements, we have a conservation of mass because we're not making any new elements along the way in the chemical reaction. We're also not losing any elements along the way. Once again, the only thing that's happening is they're just basically rearranged into new compounds on the product side from where they started. So you do need to know these sort of points. You need to know the idea that atoms maybe are not indestructible, and atoms of the same element are not identical to each other. Those are kind of 2 parts of it that, again, are not really correct. Now, he sort of pictured compounds as a collection of atoms, and here we have nitrogen and oxygen together. And again, depending on the arrangement of those elements, all 3 of these sort of compounds here only contain nitrogen and oxygen, but they all do have sort of different properties. And that happens because, in some cases we got different numbers of nitrogens, we have different numbers of oxygens. But they will always sort of come together in really a ratio that, in terms of their mass, that is the same. They kind of come together in whole number ratios. So, for example, if we look at these first 2 here, this is 1 nitrogen and 1 oxygen. This nitrogen is about 14 grams. and this oxygen is about 16 grams. And if we just kind of do the ratio of, say, oxygen to nitrogen here, the ratio of oxygen to nitrogen, take your 16 grams divided by your 1401 grams, and you'll end up with a ratio of 1.14, right? Now here we have a couple of extra oxygens in this one, or an extra oxygen, and here this guy would still be 14 grams. Each of these oxygens would be 16, and there's two of them, which would give you 32 grams. And if you take the ratio of oxygen to nitrogen here, you got 32 grams divided by 1401 grams. And that's going to give you a 2.28 in terms of its ratio. We got twice the oxygen in this one as we do this one. If you take this 2.28 divided by 1.14, that's going to give you that ratio there of a difference of 2. So they always come together in sort of a whole number ratio. So that's also something, that's the law of multiple proportions, it's sometimes referred to. But basically, atoms will come together in really these whole number ratios. So ultimately, as we talked about kind of earlier, you'll never get like a quarter of an atom coming together or a half atom. They always sort of come together in these kind of whole number ratios, especially by mass, as you can see here. They kind of join together to sort of maintain that. All right, so let's talk a little bit about the structure of the atom. Atoms, as you probably are aware of, do contain certain particles which are important to it. And based on Dalton's atomic theory, the atom was defined as the basic unit that could come into chemical combination. And a lot of investigations really show that although atoms are extremely small, they do contain an internal sort of structure. So even though overall they're really small, they actually have even smaller parts that make them up. And these are what are sometimes referred to as subatomic particles. And there's three types of subatomic particles that we'll talk about. We have protons, which you may be familiar with, are positively charged particles. There are electrons, which are negatively charged particles. And then we also have neutrons, which basically have no charge. And these three particles are pretty much what makes up all the atoms for these elements: protons, electrons, and neutrons. And what we're going to talk about are some experiments that helped us better understand some of the properties of these three sort of subatomic particles: protons, electrons, and neutrons, and also gave us a good idea as to perhaps where they are located within the atom. So the first thing that we're going to, our particle that we're going to kind of explore, is the electron. And I would say that when we do or look at the experiments that helped us understand the atom, really radioactive sort of particles were used a lot to really help us understand the nature of an atom. And let's talk a little bit about some of those, and we'll see it, I think, in a second. But just three sort of important particles, kind of radioactive particles, that really helped us along the way in some of these experiments we're going to talk about. The first one is alpha particles, and that's abbreviated with an alpha symbol. These are positively charged radioactive particles, and they are essentially the helium nucleus, sometimes symbolized like this in one of two ways. We'll talk about what those numbers represent shortly in this chapter. But basically, it's a positive radioactive type particle. There's also beta particles, which are used. Beta using the beta symbol. And these are really negative sort of particles. So these are negatively radioactive particles. They are essentially like an electron here, sometimes symbolized like that, or like this as well. Now, the last one is gamma rays. And gamma rays are just basically pure energy. They have no charge. So for the most part, alpha, beta, and gamma kind of very similar to ultimately protons, electrons, and neutrons. And they were used a lot in a number of experiments that helped us understand sort of the structure of the atom. Now, a principle that pretty much comes across a lot in chemistry and always sort of is talked about is what's sometimes referred to as electrostatic attraction. And electrostatic attraction is a fancy way of saying opposites attract. So if you are a positive thing, you are going to be attracted to a negative thing. So these guys are going to be attracted to each other. But if you are a positive thing and a positive thing, they do not like to be near each other. They will repel one another as opposed to this attraction. And if you are a negative thing and a negative thing, they also will repel each other, right? As they say, much like in life, right? If you're around a positive person and you're a positive person, that's just too much positivity happening there in the same time, right? Two negative people that want to be near each other. So they always say, try to find somebody that compliments you, right? So maybe a positive negative attraction there is what happens. But that is a basic principle here in chemistry. It is the basis of ionic bonding, as we'll talk about. It's a basis of a lot of things here. So they can use this sort of attraction to really understand what's going on. And there's also, as we will see, I think there's a slide, but I'll just kind of pop it up here as well. Um, they oftentimes will use things like electrical fields or magnetic fields because these things do have charges. And things with charges are going to be attracted to things like an electrical field or a magnetic field. If you had an electrical field where, one side was positive of that field and one side was negative of that field, and you shot a particle through that electrical field, and that particle, very badly drawn there as my thing moved, kind of bent upwards, you could probably make the assumption that that particle you just shot through that field is what type of charge? It should be negatively charged, right? Opposite's going to attract, so it's going to kind of bend up towards the negative or the positive side of the field. If you shot something and it kind of bent down towards the negative side, you could also make the assumption that probably that thing is more positively charged, right? Because it's going to be attracted to it. And obviously, if you shot something and it was sort of unaffected by anything, the electrical field, it probably had no charge associated with it. So a lot of the experiments did take advantage of things like electrical fields and magnetic fields and things that have charges in a lot of these experiments. A magnetic field works the same way. You kind of have a north pole, south pole, and things are attracted kind of similar that you see in an electrical field. So one of the earliest sort of experiments to sort of explore the nature of an electron was done with the discovery of the CRT, which is the cathode ray tube. And the cathode ray tube, kind of a drawing there on the bottom, has basically two sides. It has really a negative side and it has a positive side. And what happens is we have a stream of negatively charged kind of electrons. And because they're negatively charged, they're going to be moving away from the negative side of the CRT, and they're going to want to be heading towards the positive side because that is how they're attracted. And this CRT tube will have this stream of these negatively charged particles. And in the older days, if you will, or maybe you still have some TVs or seen some TVs, older TVs used to have CRT tubes in it. That was through picture tubes, right? And you would actually call the repair guy down to your house. You take the back of your TV off, it would repair it and all that good stuff. You just didn't go to Costco and grab a new one and throw it in the back of the truck. Obviously, flat screens and screens like we have and TVs like we have today don't have CRT tubes in them. But maybe a family member, or maybe you still have. Like, used to be on the floor of the TVs, big boxes they were in. Also, computer monitors, not like this one, but the older kind of computer monitors where there's like a big back in it. If you ever seen one of those, also a CRT monitor as well. They have those tubes. And what they would do is put some type of fluorescent material at the end of the tube there, and you can actually see where the beam's actually hitting. It sort of highlights it where it actually will hit the end of the tube. And that is a cathode ray tube, as I mentioned, got these negatively charged particles heading to the positively charged plate. And again, some type of fluorescent sort of material will allow you to do that. As we talked about, the advantage of this is something like a magnetic field, which is our North Pole, South Pole, and also our electrical field, as we just talked about a second ago. We can use these sort of things in conjunction in these experiments and really get an idea as to perhaps what type of charge we're looking at. Or if we know the charge of it, we could also manipulate the charge right in, kind of make it kind of do our will, if you will, either bend towards the positive or negative. This is a classic CRT tube here. Let's see if it'll play, maybe. Maybe. And this one, I think is the one.
A cathode ray or Crookes tube. It produces a beam of electrons, as do television sets and computer monitors. A luminescent material has been painted on part of the inner surface of the tube. It produces light when electrons strike it. The electrons originate at the cathode of the tube. The long, thin object entering the scene is a bar magnet. The position of the bright spot on the screen can be changed by moving the magnet near the beam of electrons. This process is analogous to adjusting a television picture.
Obviously, you could see charged particle affected by a magnet and also would be affected by an electrical field. So one of the earliest sort of descriptions or properties of an electron was done by a guy named Thomson. And J.J. Thomson used the cathode ray tube to sort of investigate the electron. There he is. There's his tube right there. And one of the things that came out of Thomson's experiment with the CRT is he was able to figure out the charge to mass of an electron. So doing some calculations, he was able to figure out the charge to mass of an electron. It is negative 1.76 times 10 to the 8 coulombs per gram. Coulomb is a unit of electrical charge. Grams is the mass. So again, charge to mass of an electron in this case. So one of the earliest sort of discoveries, if you will, about an electron was this charge to mass discovered by Thomson using the cathode ray tubes. And obviously you need to know that. You don't necessarily need to know the actual number, but you do need to know Thomson used the CRT tubes or cathode ray tubes to figure out the charge to mass of an electron. Now, sort of another really important experiment in terms of our electron was one done by Millikan. And Millikan did an experiment, which is sometimes referred to as the oil drop experiment. Much like the name implies, he dropped oil droplets into a chamber. And this chamber had an electrical field in it. So it has some charged plates in it. And he atomized his oil droplets. And what happened was there's this little kind of hole right about there where the oil droplet would go into this electrical field sort of chamber. And the oil droplet would obviously start to fall based on gravity there. And as it did, it would pick up a charge. And what Millikan was able to do in his experiments was he was able to adjust the electrical field in such a way that basically the oil droplet just kind of hung out there. So it didn't fall, it didn't go up or down. It's kind of almost able to dial in the electrical field in such a way that it would basically suspend the oil droplet there. Maybe that'll play it there, I think, maybe. Let's see. There it is. So there goes the oil droplets, again, through the little hole, adjusting electrical field, going to kind of keep it there. And what he was able to really figure out from this experiment was the charge of an electron. So this was another important sort of advancement in our understanding of the electron. And he determined that the charge of an electron was minus 1.6 times 10 to the minus 19 coulombs. And That's really important because if you think about these two experiments here, we have Thomson, which had the charge to mass of an electron. We have Millikan with the charge of an electron. Using the sort of results of both of these experiments, we're able to actually determine the mass of an electron through calculation here. So we have the charge. If we take it and divide it by the charge to mass of an electron, charges cancel, we end up with the mass of an electron. So if we take those two sort of important experiments and put them together and take our numbers, we do end up with the mass of an electron, which is approximately 9.09 times 10 to the minus 28. Some books will do 9.11, but we'll go with this one here. Seems pretty good. And that is how many grams there are in terms of the mass of an electron. Now, when we look at that number, is that a really large number or a small number? That's actually a really small number, right? Because it's a negative 27 or 28. So that is 28 zeros to the left, right? So it's going to make it a really, really small number. By the way, that would also be 9.09 times 10 to the minus 31 kilograms. So sometimes it's given in kilograms. So 31 kilograms. And like I said, some books will use nowadays 9.1-ish in terms of that number as well. So in terms of our electron, we now have some important information. Obviously, it's negatively charged. Using the cathode ray tube, Thomson was able to figure out that charge the mass of an electron. Millikan, with his oil drop experiment, was able to figure out the charge of an electron. Putting those together, now we're able to figure out the actual mass of an electron. Obviously, you need to know those things. Any questions on that so far? So now that we have some understanding of the electron, we did think, obviously, there was some other sort of particles involved in the atom. So now we're going to talk a little bit about the proton. And by the early 1900s, there was a couple of things that was really clear about the atom. It obviously contained electrons, and we have some information, obviously, about some properties of the electron, but it was also electrically neutral. And in order for something to be neutral, the atom, we know that it contains these negatively charged electrons, which are negative. It would have to have something that would be positively charged to sort of counteract. And for sure, we know there's got to be something around the atom or in the atom that is going to be positive charged to balance out the negative charge that we do see for our electrons. And around the turn of the last century, the accepted model of the atom was actually one that was proposed by Thomson. And Thomson basically said that the atom is this sphere of positive charge. So the atom has a bunch of positive charge, really just diffused and spread out over the entire atom. So we have all this positive charge kind of spread out. And the sort of Thomson's model was, in addition to this positive charge just really spread out all over the atom, embedded inside the atom were these negatively charged electrons. So sort of embedded inside the atom were these negatively charged electrons. And most of the mass of the atom was a result of these negatively charged electrons. And this is commonly referred to as the plum pudding model of the atom because it was thought that is a dessert of obviously pudding and some raisins. And the pudding was thought to be kind of like, oh, that's probably like all the positive charge kind of spread out over the atom. Raisins kind of embedded inside the pudding there is like the electrons, how they're sort of embedded inside. And this was sort of an early version of the atom, which looks something like this, which once again is All positive charge really spread out over the sphere, electrons embedded inside most of the mass of the atom as a result of these electrons. Now, this was sort of the accepted model of the atom until really the next major sort of discovery happened, and that happened with the world famous gold foil experiment. And the gold foil experiment was done by a guy named Rutherford, along with Geiger and Marston, but most people just refer to Rutherford in this case. And Rutherford did the gold foil experiment. And in the gold foil experiment, he used pieces of gold foil and other metals. And what he did was he shot these radioactive particles, these alpha particles, at these pieces of gold foil. Again, these alpha particles are those positively charged radioactive particles, so those heavy sort of positively charged particles. And he shot it at pieces of gold foil. Now, what he expected to happen and what actually happened were really two different things. So if we kind of go with the assumption of what is happening at this point, which is we have this plum pudding model that we just saw on the previous slide there. We got this nice sphere of positive charge all spread out. We got these electrons sort of embedded inside. And now what basically Rutherford is doing is he's taking these alpha particles, which are positively charged particles. So basically the idea here is we're going to take something that is positively charged and we're going to shoot it at this big spear of positive charge pudding, basically all spread out, right? So if you think about it, right, if this was like my atom and this was like all the positive charge, and I held like say this side of the paper and somebody held the other side of the paper really, really tight, and we shot this pin which was moving really, really fast, right? It probably would be able to punch through this paper, right, and kind of punch out to the other side. There would be some deflection as it did that, as it sort of pops through the paper. And that's sort of what they expected to happen. They expected when they shot these positively charged alpha particles that there would be some deflection. Now you're shooting something that's positive at something that is positive, right? So that blue is all positive in there. So there's going to be some repulsion as they hit each other, but these alpha particles are heavy, they're moving really fast, so they're going to be able to kind of punch through that with a little bit of deflection as they kind of bounce through it. Now, they were really, really surprised when they did this experiment was when they shot the alpha particles, pretty much, kind of no problem, right? Most of them went through undeflected. So most of them just sailed through undeflected. Another really interesting thing that they saw was every so often, although we had these guys that were moving sort of undeflected, every so often these alpha particles would bounce off at these really large angles. So every so often you would see these alpha particles that were shot at the atom basically bounce off at these really large angles and sometimes even head back, kind of where they were shot from. And that was really surprising based on the plum pudding model because they felt the positive charge should be spread out. They should have no problem really passing through there. There should be some deflection. But what they saw was, again, most went through no problem. Most were undeflected. Every so often we had these things basically bouncing off at these really, really large angles. So if you think about a couple of things, right? If we think about first off, what does that mean if the alpha particles sail through undeflected? What did they hit if they weren't deflected at all? They pretty much hit nothing, right? So nothing was in their way. So if I took my alpha particle pin and I threw it that way, it's going to sail fine, right? Because there's nothing in the way until I hit the door, obviously. But if there's nothing there, it's going to sail fine and nothing's going to happen. Now, that explains, like, okay, it obviously hit empty space because nothing happened to those particles. What would make the alpha particles bounce off at these really large angles? They had to hit something that was what type of charge to make them bounce off pretty strongly like that? Yeah, they would have to hit something that actually is positively charged, right? And that's because these alpha particles are positively charged. They would have to hit something that was very, very densely positive in order to make those positively charged alpha particles bounce off at those big angles or come back to the source. Remember, right? Things with the same charge repel each other. They don't want to be near each other, so they want to bounce off. If it was negatively charged, it would actually just stick, right? It would kind of stick right to it, right? So it wouldn't go through and it wouldn't bounce off. It would just kind of go, cool, I'm happy. I found something negative. So these alpha particles had to hit something that was very, very positive to make it bounce out. And this really basically made the idea of the plum pudding model not so correct, right? So obviously they had to move away from the plum pudding model and come up with a new model of the atom. So if you think about the plum pudding model in this paper example, right? And if this was all the positive charge, all spread out, right? But instead of the positive charge being all spread out, if I took all the positive charge and basically folded it up, however many times you could fold up a piece of paper, was it like 7 or 9 before you can't do anymore? And my positive charge is no longer all spread up, but all concentrated right here, right? Now if I try to take my alpha particle pen, it bounces off at a angle, right? Sorry about that. And it doesn't go through undeflected. It hits something that's going to make it go in the opposite direction. Thank you very much. And that means that they did have to kind of move away from the plum pudding model as the result of this experiment and come up with a new model of the atom that we're going to talk about here shortly. Any questions on that there? All right. Whoops, let me go back and actually show you that there. I think that one's it.
In 1910, Rutherford and his co-workers were studying the angles at which alpha particles were scattered as they passed through a thin gold foil. Most of the alpha particles passed through undeflected. However, a few were found to be scattered at large angles, some even back in the direction from which they had come. This meant that they had collided with an object much more massive than the alpha particles themselves, yet so small that only a few alpha particles encountered them. This atomic level view shows what is happening. Most of the atom is occupied by the low mass electrons. The nucleus is small and massive. When an alpha particle encounters a nucleus, it is scattered at a large angle.
So again, an example here of the experiment. You can see most of them just kind of sail through no problem, but we do get these guys bouncing off at these large angles. Again, makes us think that the plum pudding model is not correct, where we have the positive charge spread out, but it's more a concentrated, very dense positive core within the atom, as you mentioned in that animation there, which is obviously known as the nucleus. So the nucleus within the atom is where we find this really dense positive core basically happening. All right, so as we kind of talked about these alpha particles scattered. Again, on the left is what they thought would happen. Again, deflection as it goes through. On the right here is what they really observed, these large angles, most of them going through not too bad in terms of their deflection. So basically, we had to sort of throw away, if you will, the Thomson's model, the plum pudding model, and come up with sort of the modern model of the atom and the Rutherford model. And the Rutherford model and the really current model of the atom is again, mostly empty space. And that is accounted for based on the fact that we saw those alpha particles really not have any problem. They weren't really deflected. So there's a lot of empty space within the atom. It has a dense positive core, which is the nucleus. And later found that obviously the protons are found in the nucleus. And later on in 1930s, neutrons were also found in the nucleus. Again, in the 1930s, they found that out a little bit later on. We'll put it here for now. And the other really major difference between the plum pudding model and Rutherford's model of the nuclear atom is the mass of the atom. So in Thomson's model, the Plum Pudding model, it was believed that the electrons were actually most of the mass of the atom, but most of the mass of the atom is actually the nucleus. So those are the major differences and really the current model of the atom. So you do need to know that. So you do need to know Rutherford's experiment, what he did. You need to know what he expected to happen based on the Plum Pudding model. Obviously, you need to know the Plum Pudding model, what it was. Uh, you need to know what he actually saw and discovered, and obviously the version here of the atom, or the Rutherford version and the modern version of the atom. Any questions on that? By the way, the electrons are out from the nucleus at some distance, right? So they're flying around in that empty space is really where we find electrons. Is there going to be some attraction between the electrons and the nucleus? The answer is yes, because electrons are negatively charged, the nucleus is positively charged. That is why your electrons that are flying around in the empty space just don't all leave, right? Just don't fly away. They're attracted and sort of pinned, if you will, to the atom based on their attraction to the nucleus, that positive charge that happens in the nucleus. Also, as we'll talk about, why some electrons are super pinned to the nucleus and not involved in things like bonding and stuff like that because they're very close to the nucleus, as opposed to ones that are further away from the nucleus where you can remove them from the atom and things like bonding and stuff like that. They do have an attraction, but not as strong. Any questions on that there? All right. So here's just a table of some of the experiments and the results that we talked about. It's a good little summary table of sort of the understanding of the structure of the atom. Now, the protons, as we talked about, found to be in the nucleus and positively charged. And experiments show that the protons have a mass of 1.67252 times 10 to the minus 24 grams. Again, if you remember, our electrons mass was like 909 times 10 to the minus 28 grams. Which one is heavier, the proton or the electron? The proton is. So remember, if you're comparing negative exponents, the smaller negative exponent is actually the larger number because you're not doing as many zeros to the left. So it makes it a bigger number. So actually, the proton is around 1,840 times heavier than any electron flying around. This also sort of reinforces the idea that came out of Rutherford's experiment that no, most of the mass of the atom is actually the nucleus, and that's because protons are in the nucleus, and any proton in the nucleus is about 1,800 times heavier than any electron that's flying around the nucleus. So most of the mass of the atom in that nucleus where we do find those protons. Now, at this stage of the sort of experiments, scientists basically had this understanding of the atom. The nucleus comprised most of the mass of the atom, but actually only basically took up a very small volume of the actual atom itself. So although the nucleus is the most massive part of the atom, it's actually kind of like the smallest part of it as well itself. So you could think of the atom like the Super Bowl, that's still thinking of Super Bowl, Superdome, or any type of big football stadium. If you've ever been to the Superdome, seats very, very high. You feel like you're falling out of your seats when you're sitting in the seats. That's not good. But you can think of the atom as a big football stadium, and really like a marble on the 50-yard line in the middle there is the nucleus. So big empty space, small little volume that's made up of those protons, which are positively charged, and most of the mass of the atom. And again, those electrons flying around in that big kind of empty space all around it. Now, for a lot of time, there was always a belief that in addition to electrons and in addition to protons, there was another sort of subatomic particle involved in the atom, and that was the neutron. And it really wasn't until 1930s that a guy by the name of Chadwick basically discovered the neutrons. And Chadwick did a lot of experiments that involved beryllium with alpha particles. And what he kind of noticed coming off of these experiments was there were some particles or rays that were very similar to gamma rays. And if you remember, gamma rays have no charge. And later experiments show that these rays consist of particles that were neutral and had a mass of 1.67495 times 10 to the minus 24 grams. If you compare that to the proton's mass we just saw, actually the neutron barely, if you go out a few decimal places, beats out the proton as being the heaviest of all three particles. They're very, very close to each other. That also would mean that the neutron is also around 1,800 or so times heavier than any electron flying around. We call this the neutrons. So within the nucleus, we have protons which are positively charged, neutrons which have no charge, and both the protons and the neutrons are about 1,800 times individually heavier than any electron that is flying around in that empty space. And the order of masses is neutron is the heaviest, proton pretty darn close to it, and then the electron is the lightest in terms of the mass of that. As we will talk about and as we just did, there is an attraction between the negatively charged electrons and also the positively charged nucleus. Electrons, by the way, do not travel in pretty circles. They travel pretty randomly around the nucleus, so they don't travel in these pretty circles or anything like that. This discovery of neutrons also, once again, reinforces the idea that came out of Rutherford's experiment that the nucleus is the heaviest part of the atom, because in the nucleus you find protons, in the nucleus you find neutrons, and once again, both of those particles individually are again 1,800 or so times heavier than any electron. So most of the mass is composed of those particles, which are found in the nucleus. Any questions on that? And again, here's the comparison. As you can see, protons and neutrons fairly close, but you get out to about the third digit there. The neutron just barely edges it out. Electron way far behind in terms of mass, the lightest of all those particles. All right. Let's talk a little bit about the modern structure of an atom. Is sort of the idea there. You can see the nucleus in the middle, very, very small volume. All that sort of red or smear of pinkish type color is really all the empty space. And that is where we have electrons. By the way, this is what is sometimes referred to as an electron density map. You can kind of see it up there on the screen, but it's actually darker pinkish here. Maybe that's not the best color. And it gets kind of lighter pink as you kind of go out from the nucleus. And the darker the color pink is, a higher probability of finding an electron in that area. So you can see the darkest areas around the nucleus, which we would expect because, again, of that attraction force. And it gets a little bit lighter as you go out far away from the nucleus. You could still, as you can see, find some pink out there in the edges, and you can still find electrons out there, but they're not going to, as we'll talk about in later chapters, be held anywhere near as tightly as those ones closer to the nucleus. All right. Any questions on the atom and those things? So again, you need to know those experiments we talked about, what they were, what happened, the results of them. You need to know about the Plum Pudding model, what it was. You need to know, obviously, about Rutherford's model of the atom that came out of it, and the kind of current version, which is Rutherford's model. Any questions on that? All right, so continuing on here, the chemistry of atoms does come from its electrons. So if you think about sort of the structure of an atom, that is pretty much going to be the first things that come in contact with each other. So if we have an atom here, and we have an atom here, and since we have electrons flying around on the outside, when these two guys come together, they really are going to be the first things to sort of come in contact with each other. And it is the basis, as we'll talk about in the bonding chapter, of all bonding. Sometimes that results in those electrons going from one atom to the next in an ionic bond, and sometimes it results in them just sharing electrons between the two atoms in a covalent bond. But that is what's involved in a chemical reaction. Again, the only thing that changes is those atoms being bound to something else, and bonding is all about electrons. So bonding only involves electrons, does not involve anything in the nucleus. So when we look at the nucleus of an atom and a chemical reaction, or protons and neutrons, not involved. Only those outer electrons involved when atoms come together. So this is really important, as we'll talk about shortly, because we don't do anything with the nucleus. That is also the main reason why in a chemical reaction we don't change elements. We keep the same elements because it's just the electrons involved that occur. So let's talk about some properties of the atom. This helps us understand that as well. And that is atomic number, mass number, and isotopes. We will start with atomic number. The atomic number is abbreviated sometimes as a Z. And the definition of the atomic number is the number of protons there are in an atom of an element. Now, because an atom only contains three particles, protons, which are positively charged, electrons, we know how many positive charges we have. And if we have a neutral atom, that will also tell us how many electrons there are, right? So in order for something to be neutral, all the positive charges, all the negative charges has to cancel each other out. So if we know the number of protons and it is neutral, the atom, we will also know the number of electrons. So it will tell you that information as well. It is important, though, to remember if you were asked a question of what is the definition question, the correct answer is the number of protons, and that is it. Second to that definition is if it's neutral, it will also tell you the number of electrons, but that is not part of the definition of an atomic number. Now, where can we find atomic numbers? I don't know. If we look on the periodic table, maybe there. So we take a look at the periodic table and we look at the number up on top of the element. That is the atomic number. So you can find the atomic number on the periodic table right above the element. If you look at the three periodic tables we have in this room, actually there's three periodic tables on the wall. I don't know why I didn't put it on the back walls, why not? But if you look at any of those periodic tables on the walls here, you will see that do any of the numbers on top repeat? They do not. So if you look at all the numbers on top, there is not a number that repeats. And that is a really important thing. And that is because every single element will have its own unique atomic number. And that also means a couple of things. Because every element has its own unique atomic number, because the definition of atomic number is the number of protons, that means each element will have a different number of protons. So for example, hydrogen here. If it is a neutral hydrogen atom, hydrogen would have one proton that's positive, and it would also have one electron that's negative. One positive guy, one negative guy gives you no charge overall. It is neutral. Right? Now, if you look at the example there for nitrogen, number 7 right there, that tells you in a neutral nitrogen atom, you will have 7 protons, which are positive, and because it's neutral, you would also need 7 electrons to be negative. 7 positive things and 7 negative things give you no charge overall, and it would be neutral. Could I ever have a oxygen atom that has 9 protons? Is it possible to have an oxygen atom that has 9 protons? No, because when you go to the periodic table and you look up oxygen, it is number 8, which means in order for it to be oxygen, it needs to have 8 protons, right? And obviously, if I had 9 protons, it is not oxygen. It is what element, by the way? It would be fluorine, right? Number 9 would be fluorine. So the atomic number is really important because if you know the atomic number, or if you know the number of protons, or frankly, if you know the number of electrons and it's neutral, you will also know the number of protons in that case. You will know what element you are dealing with by just going to the periodic table and finding that number. So that is really important. This is also why, as I was just talking about, the most important the most important particle in terms of what element it is which one? The proton, electron, or neutron? It's the proton, right? So the proton is the most important subatomic particle to know what element you're dealing with. That is why in a chemical reaction where we do not touch anything in the nucleus, that's why we have the same elements we start with and the same elements we end with, because we never touch the nucleus, we don't touch the protons, we don't touch the neutrons, and because if we started with a carbon, it has a certain number of 6 protons, and it will end up with 6 protons, and that keeps it carbon on both sides, because it's only the electrons. You can do as much as you want with the electrons. As long as you don't touch that nucleus, you don't touch those protons, you will never change the element. That is also why if you take Chem 1B and you get to that nuclear chapter, in nuclear chemistry, we do nothing in nuclear reactions other than change protons to neutrons, neutrons to protons. We do everything like in the nucleus. And that's why in nuclear chemistry, we actually don't have conservation of those elements, because we do nothing but change those protons and neutrons all the time. But in a chemical reactions, like I said before, like we talk about in this class in 1A, the only thing we play with in chemical reactions is electrons. We never touch the protons. And that's why we end up with the conservation of those elements in a chemical reaction, and also why you have to balance the equation when you're using a chemical equation. Any questions on that there? Yeah. The next kind of important number is the mass number. And the mass number is sometimes abbreviated as an A. And the mass number is actually the number of protons and the number of neutrons. So the mass number is your number of protons plus your number of neutrons. Your atomic number, as we just talked about, is your number of protons. The importance of the mass number and the atomic number is this. If I take the mass number and I subtract it from the atomic number, protons go away. That will give me the number of neutrons. So if you take the mass number and you subtract it from the atomic number, you will end up with the number of neutrons you have in an atom. When you calculate any of those things, you calculate the mass number, you calculate the atomic number, you calculate how many protons, electrons, or neutrons an atom has. They all should be positive whole numbers. So that brings me to the important question of, I look at my periodic table. I find hydrogen, which says 1 on top, says 1.008 on the bottom, 8-ish on the bottom. I know this is the atomic number. Is this the mass number? The answer is no. And it is not the mass number, because the mass number, the atomic number, the protons, electrons, and neutrons need to be what type of number? They all need to be whole numbers. That is not a whole number. That is what is known as, we'll talk about, the atomic mass, but that is not the mass number. If you take a look at the periodic table, all the numbers underneath the elements, pretty much none of them are whole numbers. They're all decimal numbers. That is a good way to remember that. You do not want to be the person on the test that writes the number on the bottom there, which is a very common answer people give. Also, the reason they give it is a lot of times when you calculate like the mass number or something like that, it's very close to the number you see on the bottom because it's made up of protons, electrons, and neutrons. So sometimes people think, oh, they must have just like rounded the number or something, right? And that's not the case. So the only number you can find on the periodic table is the atomic number. The mass number is not found on the periodic table. You will be given enough information in the problem to calculate the mass number, atomic number, number of protons, electrons, and neutrons. But again, the only thing you get from the periodic table is the atomic number. Any questions on that there? Now, isotopes, as we talked about, are the same element, but they have different masses. So because they have to be the same element, that means, as we just talked about, the number of protons has to be the same, right? It's the protons that determine the element. So because they have different masses, they actually means they have different numbers of neutrons. So isotopes are the same element, but they have different masses. They have different masses because they have different numbers of neutrons. They have the same number of protons, otherwise they would not be the same element. Every single element will have protons, electrons, and neutrons. The exception is hydrogen. Hydrogen has only a proton and only an electron. Hydrogen does not have a neutron. And when we look at hydrogen, it has some isotopes. There's deuterium, which doesn't sound like hydrogen, but it's an isotope of hydrogen. There's tritium, which is the radioactive version of hydrogen. And one of the ways that we write isotope symbols is what we see down here. We take the element symbol, and to the top left, we write the mass number, and to the bottom left, we write the atomic number. So that is a very common way that we write symbols for isotopes. Top number, mass number, which once again is our number of protons plus our number of neutrons. And bottom number is our number of protons, which is our atomic number. Any questions on that there?